Hey everyone, and welcome back. Today we're diving straight into our Chapter 3 explainer, and we are tracing a truly wild journey, the life cycle of a sound wave. From the absolute pin-drop silence of the cosmos to the blaring speed of noise right here on Earth, we're going to break down the invisible physical forces that let us hear everything from a tiny whisper to a booming thunderstorm. So, if you're ready to completely change the way you think about the noises around you, well, you're in the right place. Let's get into it.
So picture this. You've got astronauts working up in orbit. They're just inches apart, maybe collaborating on some highly complex repair job outside their spacecraft. But here is the crazy part. If their communication headsets were to suddenly fail, no matter how loudly one astronaut yelled to the other, they wouldn't hear a single thing. Literally nothing. They are right next to each other, yet totally separated by this impenetrable wall of silence.
Which begs the question, right? Why is space completely silent? It's a profound thing to think about. And to solve this mystery of why those astronauts can't hear each other speak, we actually have to take a step back, because we can't really understand the silence of space until we figure out how sound is born right here on our home planet. We need to look at the mechanical engine behind every single noise we experience.
All right, Phase 1, the birth of sound.
It literally all kicks off with a simple vibration. In scientific terms, this is just a speedy to and fro movement that generates sound. This rapid back and forth motion is the foundational concept for understanding, well, everything we hear. Without this physical movement, the whole universe is just entirely mute.
Now you might be wondering how we can actually see this totally invisible phenomenon in action. Well, try this. If you take a standard audio speaker, connect it to a dry cell battery, and place tiny, lightweight pieces of polystyrene right on top of it, something awesome happens. When the sound is generated, the speaker cone physically moves to and fro, and this speedy movement violently throws those polystyrene pieces right up into the air. It perfectly visualizes those otherwise invisible vibrations. So sound isn't just some magic trick. It's a physical, mechanical force pushing against the world.
Actually, scratch that. You don't even need a speaker to test this. You can feel this happening right now. Seriously, place your fingers lightly on the middle of your throat and just say something. Feel that light trembling? If you speak a little louder, you're going to feel that tremble increase. What you're feeling right there are your vocal cords. They're tiny membranes inside your throat that are rapidly vibrating. Your own voice is just the result of that exact same speedy to and fro movement.
Moving on to Phase 2, how instruments make music.
Think about it like this. Every single musical instrument is essentially just a highly engineered vibration machine. If you pluck a guitar, it's the tightly wound strings doing the vibrating. If you strike a drum or a tabla, you're causing a stretched membrane to rapidly move back and forth. And in a flute, it's actually a literal column of air inside the tube that vibrates. So it's different parts, but the exact same core scientific principle across the board.
We humans have spent centuries coming up with wild and diverse ways to make things vibrate. Whether it's the heavy strings of a cello, the tight skin of a bongo drum, or the complicated brass tubing of a saxophone manipulating air, all sound sources fundamentally rely on creating a disturbance, a physical vibration, to create their unique sounds.
Okay, let's jump into Phase 3, the need for a medium.
So, back to our astronauts. If sound is just vibration, why does it completely fail in space? Well, because sound is a traveler that desperately needs a physical road to travel on, and we call this road a medium. Down here on Earth, we are constantly surrounded by physical mediums. The gases in our air, the liquid in our oceans, the solid ground we're standing on. When a vibration happens on Earth, it bumps into the particles of these mediums and passes the energy along, kind of like dominoes falling. But space is a vacuum. There's no air, no liquid, no solid matter sitting between those astronauts. Without a medium, the vibration literally has nothing to bump into. The road just doesn't exist, so the sound goes absolutely nowhere.
To prove just how important these physical roads are, we can look at some everyday applications. You know those string and cup telephones you might have made as a kid? 2 empty yogurt cups, a tightly stretched string? If your friend talks into one cup, you can hear them perfectly through the other, simply because the sound wave travels beautifully along that solid thread. Medical stethoscopes work exactly the same way. They pick up the vibrations of a patient's heartbeat and direct them through a solid and air medium straight to the doctor's ears. Back in the day, massive sound pipes were even used in ships and deep mines to send acoustic messages over incredibly long distances. A medium is just absolutely essential.
Which brings us to Phase 4, the great race, speed of sound.
Now, consider this practical, though I must strongly stress, very risky scenario.
please don't try this. But if you were to place your ear on a steel railway line, you could hear a distant train approaching through the tracks long before you'd hear the sound of the train traveling through the air. Why on earth does the exact same sound arrive at your ear at two completely different times?
It's all about density. The density of a medium totally dictates the speed of sound. In a gas like air, sound cruises at a relatively slow 330 meters per second. But drop that wave into a liquid like water, and boom, it speeds up to 1,500 meters per second. Put it into a dense solid like steel, it absolutely rockets to 4,500 meters per second. Because the particles in the solid are packed so tightly together, those to and fro vibrations pass from one particle to the next incredibly fast. That is exactly why the steel tracks deliver the sound of the train so much sooner than the loose particles in the air.
But as crazy fast as sound can travel through steel, it still has a massive rival. Let's compare the speed of sound to the ultimate speed champion of the universe, light.
You've definitely noticed sensory delays in nature before. Think about a cannon being fired from far away. The smoke and the boom happen at the exact same instant, right? Yet, if you're watching from a distance, you'll see the flash and the smoke immediately, and then you wait. It takes several seconds before you finally hear that explosive boom. The exact same thing happens with thunderstorms. You see the lightning flash instantly, but you always have to wait for the thunder. This happens simply because sound, even on its absolute best day, completely loses the race to light, every single time.
So let's pull all this together. By tracing this journey in our explainer today, we've really unlocked the absolute core rules for how sound behaves in our physical world. We know it requires a speedy vibration. We know instruments manipulate these vibrations using strings, membranes, or air. We know sound desperately needs a physical medium to travel, which is exactly why the vacuum of space remains eternally silent. And finally, we know that dense solids provide the ultimate fast track for these acoustic waves.
The next time you listen to your favorite song or just hear the wind rushing through the trees outside, remember what we talked about today. The beautiful symphony of our world isn't magic. It's simply an invisible, mechanical journey of physical vibrations bumping against one another, particle by particle, just to reach you. Which leaves us with one final, pretty wild thought. If the vacuum of space were suddenly filled with a medium like air, what do you think this massive, explosive, raging universe would actually sound like?